Welcome to AI Paper Podcasts. Today we're diving into a paper that's really set to transform how we tackle some pretty big challenges in AI. PyG 2.0, Scalable Learning on Real-World Graphs. This is a comprehensive update to the PyTorch Geometric framework, and it's designed specifically to, well, conquer the complexities of real-world graph data. You know, graph neural networks, GNNs, they're popping up everywhere these days, connecting friends on social networks, mapping out complex molecular structures.
Right, they're incredibly versatile.
But let's be honest, real-world data isn't usually nice and clean. It's often messy, it's constantly changing, and sometimes it's just absolutely massive.
Precisely. In PyG, PyTorch Geometric, it's been a leading framework for GNNs since, 2019? Especially known for its flexible message passing scheme.
Yeah, it's been super popular.
But, the early days of GNN research mostly focused on smaller, maybe more controlled benchmarks. The field has just evolved incredibly quickly, and the demands on graph learning systems have really scaled up significantly, pushing way past what those initial frameworks were really built for.
Okay, so our mission today is unpack how PyG 2.0 actually confronts these real-world challenges head-on. We're going to look at how it transforms GNNs from, maybe, academic tools into true powerhouses that can handle industrial scale problems. All right, for those of you tuning in, maybe just for a quick hit, here's a lightning summary of what PyG 2.0, Scalable Learning on Real-World Graphs, really delivers. This paper presents a, monumental update to the PyTorch Geometric framework.
Yeah, the core insights are pretty clear. PyG 2.0 makes these huge strides in scalability. That's a big one. It also adds robust native support for heterogeneous and temporal graphs, so graphs with different types of nodes and edges and graphs that change over time. And crucially, it builds in explainability right from the ground up. Architecture-wise, it introduces an enhanced setup with scalable feature and graph stores, highly optimized message passing, and seamless model compilation.
So what this ultimately means for you, the technical listener, whether you're an AI researcher or maybe an ML engineer, is you get this powerful end-to-end blueprint for building incredibly efficient GNNs. This really unlocks breakthroughs in areas like relational deep learning, even integration with large language models, letting you process graphs with potentially billions of nodes without, breaking a sweat. Stick with us as we show you how it actually pulls all this off. Okay, so we've talked about the challenges, messy, massive, dynamic graphs. Now let's dive into how PyG 2.0 actually built the foundation to tackle these.
It seems like it's gone way beyond just being a collection of GNN layers to become this true end-to-end blueprint. What's the sort of big picture here?
Right, it's really a complete rethinking. PyG 2.0 is designed as a comprehensive library built directly on PyTorch using a Tensor-Centric API.
Tensor-centric, okay. Yeah, meaning everything, your features, the graph structures, even the neural building blocks, they're all handled as tensors. This makes it feel really intuitive if you're already in the PyTorch world. Think of it less like just a box of tools and more like a modular plug-and-play system. Almost like building with advanced Lego bricks, as Figure 1 in the paper nicely illustrates.
So it's a proper framework then, allowing for flexibility, future expansion.
Precisely. The system's very thoughtfully organized into three main parts. First, there's the graph infrastructure that's all about managing the graph data itself. Second, the neural framework, which is where your GNN models and their operations live. And third, post-processing routines for things like analysis and evaluation. The real beauty of this modular design is you can seamlessly swap out components. Maybe you need a new storage solution or a different sampling strategy or even a novel aggregation function. You can swap those in without having to rip apart the rest of your system. This makes it incredibly friendly for research, for rapid experimentation, and it takes full advantage of PyTorch advancements like Torch.compile for optimization, and it leverages specialized C++ and CDA kernels through this external piglib package for, maximum efficiency.
Okay, PyG has always been known for its message passing, right? That's really the heart of how GNNs learn. But it seems like the core insight in 2.0 is realizing that optimizing this fundamental operation using intelligent data structures and compilation is what really unlocks that industrial scale. So what's fundamentally new here? What makes message passing so much more powerful?
Yeah, you absolutely hit the nail on the head there. Message passing is core, but it can easily become a performance bottleneck, especially with large graphs. PyG 2.0 tackles this with something they call the edge index tensor. It's a special subclass of Torch tensor.
Okay.
And it holds the source and destination node indices for every connection in your graph, stored in what's called sparse coordinate format, or COO.
Right, COO. So it's not just a simple list of connections, it's like a smarter container.
Exactly. What makes it smart is it holds extra metadata, like sort order, And it has this clever caching mechanism built in. This allows for really fast conversion to other sparse formats like compressed sparse row, CSR, or compressed sparse column, CSC.
CSRs and CSC, those are optimized for sparse matrix math, right?
Exactly. They're highly efficient ways to store and process sparse data with lots of zeros, which is typical for graphs. It makes computations much, much faster, especially matrix multiplications. This intelligence lets PyG choose the optimal computation path. If your edge index is sorted correctly, it can efficiently use sparse matrix multiplications, SPMMs.
SPMMs, okay.
Think of those as specialized operations designed for matrices that are mostly empty. That means way faster computation, much less memory usage, especially critical on GPUs. Plus, that caching mechanism. For repeated GNN layers, caching the CSR and CSC formats significantly cuts down overhead during the backward pass. That's huge for training speed.
That's really clever, just squeezing out performance from the data structure itself. What about how those messages get combined? Aggregation functions are pretty critical for GNN's power, aren't they?
Oh, absolutely. The choice of aggregation is fundamental.
Wow.
It influences properties like symmetry, expressive power. It's really key. PyG 2.0 makes aggregation a first-class principle. What that means is users can easily plug and play with a huge variety of aggregation functions. You've got the simple ones like mean, max, sum, but also more advanced ones like median or variance, even learnable aggregations, or unconventional ones like LSTMs.
Wow, okay.
This unification means they can centralize optimization efforts and build specialized implementations that benefit the whole framework, not just in message passing, but also in, say, global readout steps.
And real-world graphs, they're rarely just uniform, right?
Yeah.
They're often heterogeneous, different types of nodes, different types of edges, like a social network with users and posts, or a knowledge graph. How does PyG 2.0 handle that complexity?
That's a really significant point because, yeah, real-world graphs are almost always heterogeneous. PyG 2.0 provides enhanced native support for this. That includes specific data types, transformations, even graph samplers designed just for heterogeneous graphs. And what's really remarkable, I think, is that it can even automatically convert any homogeneous GNN1 built for just single types of nodes and edges into a heterogeneous version.
Automatically.
How? Through a Torch.fx Transformation. Torch.fx is this powerful PyTorch tool for tracing and modifying your code. Essentially, PyG replicates your GNN layers for every edge type, then transforms the computation graph to perform bipartite message passing over each type, followed by a custom aggregation. And it does this super efficiently, using grouped and segmented matrix multiplications, leveraging high-performance GPU libraries like C2TLS.
That sounds like a huge step forward for just adapting models easily.
But then there's PyTorch's eager mode. It's great for development, debugging, but sometimes a performance bottleneck in production. How does PyG 2.0 balance that? Yeah, they tackle that directly with robust model compilation using Torch.compile. PyG 2.0 supports end-to-end kernel fusion without graph breaks. Basically, multiple operations, complex sparse computations, feature transformations, all that can get fused into a single, highly optimized kernel.
Kernel fusion. Fewer calls, less overhead.
Exactly. You minimize memory access, fewer kernel launches. It makes message passing significantly faster, especially if you have deeper or wider GNNs. The paper actually highlights an impressive 2 to 3 times speed up in runtime on average. Table 1 shows this clearly. They really work to make their code base compilation friendly.
Wow. And just quickly on architecture, I noticed they've also integrated state-of-the-art graph transformer models.
Yes, absolutely. Aligning with, recent deep learning trends, PyG 2.0 incorporates powerful graph transformer architectures. This allows for effective learning on both scenarios. Lots of small graphs or a single really large graph. And they offer flexible positional encodings to capture that crucial structural information that transformers need.
Okay, so the neural network core is faster, it's more flexible. But let's talk about the real elephant in the room. Those truly massive graphs. Billions of nodes, thousands of features, stuff that just won't fit in memory. How does PyG 2.0 actually scale to that?
Right, this is where their infrastructure innovations really come into play. It starts with scalable feature and graph stores. PyG 2.0 introduces these new feature store and graph store remote backend interfaces.
The little backends.
Yeah, these let you seamlessly connect to any custom external storage you might have, think large-scale databases, distributed file systems, whatever, while keeping the familiar PyG training loop. The really clever part is that any distributed communication needed to get that data. PyG handles it completely transparently for you. They've neatly separated the concerns. A feature store for node edge attributes, a graph store for the structure, and a graph sampler. This modularity means you can plug in your own custom storage handling, and your core GNN training code doesn't even need to know about it.
That's a really smart design. Gives you flexibility without rewriting everything.
Yeah.
But for those enormous graphs, you often can't process the whole thing at once. You need to sample smaller bits, right? Subgraphs. How does PyG handle efficient subgraph sampling?
Yeah, subgraph sampling is absolutely essential for scaling. It drastically cuts down memory and compute costs, makes mini-batch training feasible even on billion-node graphs. PyG introduces a high-performance custom C++ sampling pipeline for both homogeneous and heterogeneous graphs, and it fully supports multi-threading.
C++ for speed, avoiding Python overheads.
Exactly. It tackles the inefficiencies you often get with pure Python implementations. And here's an interesting distinction. Some other libraries might give you layer-wise, one-hop subgraphs. PyG produces a single multi-hop subgraph.
A single multi-hop subgraph. Why that approach?
It's actually much more flexible. It allows seamless transitions between full batch and mini batch training, and it promotes a cleaner separation between your model architecture and the data loading logic. Keeps things tidier.
Okay, here's where it gets really interesting for me. When you sample a subgraph, say using breadth first search, BFS, isn't there a risk of doing redundant computation in later GNN layers? Like, nodes sampled early on might not really matter for the final representation deeper in the network.
That's a really sharp observation, and yes, that's a known issue with standard BFS subgraphs. PyG has an ingenious solution, a layer-wise pruning mechanism.
Layer-wise pruning?
Yeah. As it generates the subgraph, it progressively trims the adjacency matrix layer by layer. It basically slices the adjacency and feature matrices on the fly using the BFS ordering. The crucial part is it does this with zero copy slicing. No extra memory gets allocated. It's just creating views onto the existing data.
Very efficient.
Extremely.
Yeah.
And when you combine this intelligent pruning with their model compilation, the result is impressive, a 4 to 5 times speed up, as they show in Table 2.
Wow, 4 to 5x just from optimized sampling and compilation combined. That's massive. What about graphs that change over time? Temporal data is everywhere now.
Right, and PyG 2.0 has robust support for temporal subgraph sampling too, for both homogeneous and heterogeneous graphs. This lets you traverse dynamic graphs over time, extracting snapshots that strictly respect temporal constraints. So crucially, no future information leakage. You only see data available up to a specific timestamp.
Makes sense.
You can extract subgraphs around a specific node in a specific time, and they offer various temporal sampling strategies, uniform, most recent K elements, even annealing-based ones, lots of options.
Given all these performance boosts, especially for large graphs, is there any specific deep integration for GPU acceleration, maybe with NVIDIA's ecosystem?
Oh, absolutely. They've enabled end-to-end GPU-accelerated workflows through GraphRAG integration.
GGraph, part of Rapids.
Exactly. The QGraph page extension is part of NVIDIA Rapids, which is all about accelerating data science on GPUs. It builds on QGraph for GPU-accelerated graph analytics and sampling, and WholeGraph for distributed tensor storage on GPUs. This integration delivers really significant 2 to 8 times data loading speedups, often with minimal code changes, even on a single GPU, and it scales pretty linearly with multi-GPU setups.
So faster loading, faster sampling.
Yeah, it allows for incredibly fast bulk sampling directly on the GPU and efficient feature distribution across workers. Really minimizes those data movement overheads.
Okay, shifting gears a bit. In today's world, with these complex models, understanding why a GNN made a decision is becoming absolutely vital, right? For trust, debugging, compliance.
Definitely.
Like PyG 2.0's insight here seems to be that explainability for GNNs needs to be modular and flexible, integrated right into their unique data flow, not just bolted on afterwards. How do they tackle this tricky area? GNNs and their irregular structures make it hard.
That's a crucial point, and yeah, it's often overlooked, but so important. GNNs are inherently challenging to interpret because of those relational structures. PyG 2.0 addresses this with a universal explainer interface. Figure 2 shows this quite well. This explainer class acts like a sophisticated bridge. It connects your GNN model, the explanation algorithms themselves, and the graph data, all to generate attributions, basically scores highlighting the importance of specific nodes, edges, or features in the model's decision.
So it's not just a generic explainer, it's specifically designed for how GNNs actually work, their message passing.
Exactly. To handle things like structural explanations for graph edges, which are non-differentiable inputs usually, the explainer module temporarily alters the internal message passing. It uses this clever callback mechanism.
A callback.
Yeah, this callback lets you inject logic to, say, introduce perturbations, apply edge-level masks to reweight messages, or even capture internal attention scores if the model uses them. It's a very modular design. Researchers can focus on developing cool new explanation algorithms, and PyG handles the complex data flow, visualization, evaluation protocols, all that plumbing.
That sounds really useful. And I heard they also connect directly to CAPTEM. That's a more general PyTorch explainability library, right?
Yes, PyG offers direct CAPTEM integration. CAPTEM has a wide range of explainers, especially gradient-based methods. The challenge, again, is applying these directly to GNNs because graph inputs like edges aren't typically differentiable. You can't easily backpropagate gradients through the graph structure itself.
Right.
PyG's clever solution is the CAPTEM explainer module. It essentially wraps the GNN so that only node features and an edge-level soft mask are needed as input. This soft mask is then used by that callback mechanism we talked about to reweigh messages in every GNN layer.
So it makes the structure effectively differentiable for the explainer.
Precisely. It makes all the inputs look differentiable, allowing powerful gradient-based explainers from CAPTEM to interpret both feature importance and the influence of the graph structure itself. It's a really neat trick.
Okay, so bringing it all together, what does this mean for the real world? Beyond benchmarks, where are these enhanced PyG 2.0 capabilities actually making the biggest impact right now?
Well, these advancements are directly enabling breakthroughs in some really practical domains. A major one is relational deep learning, or RDL. PyG's strong support for heterogeneous and temporal graphs makes it a fantastic modern deep learning alternative for learning directly on raw relational databases.
You mean like treating an entire SQL database as a graph and learning from it? That sounds incredibly powerful.
Exactly. Entities become nodes, primary foreign key links become edges. PyG offers a full end-to-end RDL blueprint for this. This includes handling multimodal data through integration with PyTorch Frame, or TensorFrame. So nodes can hold numbers, categories, free text, all sorts of things, as Figure 3 shows. They also support querying historical subgraphs. The samplers can iterate over external seed nodes and timestamps, always respecting the temporal order.
Crucial for things like fraud detection or recommendations over time.
Precisely. And speaking of recommendations, they have robust recommender system support, including efficient maximum product search, MAPS, via PyIS integration, which is super fast for finding similar items in huge catalogs. This pushes link prediction GNNs beyond just simple classification towards more realistic recommendation scenarios where you don't know the candidate items beforehand.
That's really comprehensive. And how does PyG 2.0 fit into the world of large language models, LLMs? They're everywhere right now.
Right. PyG contributes here in two main ways. First, it provides great examples of using LLM embeddings within text-attributed graphs, so your GNNs can leverage the rich semantic understanding from LLMs.
Okay, using LLM features in GNNs.
And second, maybe even more excitingly, it supports various techniques for retrieval augmented generation, or RAG.
GraphRAG. Using GNNs to help LLMs reason over structured knowledge? This is where things get really interesting, I think.
Totally. As Figure 4 depicts, the GraphRAG pipeline typically starts with a natural language query. That query retrieves a relevant contextual subgraph from a larger knowledge graph. Then that subgraph is encoded using a GNN. The resulting node embeddings are aggregated and projected into the LLM's embedding space,
Feeding structural context directly to the LLM.
Exactly. It significantly enhances the standard LLM flow by providing that crucial relational and topological information. PyG supports this through extensions to its feature store and graph store, making the retrieval part highly customizable.
And here's a surprising stat from the paper. They showed a 2x increase in accuracy for GNN plus LLM graph RAG, jumping from 16% to 32% compared to just using the LLM alone.
Yeah.
That's a massive improvement. It really shows the power of combining these different AI approaches.
It truly highlights that synergy integrating structural knowledge with language models, and they even provide a handy TXT2KG class. It's an easy interface to convert unstructured text datasets straight into knowledge graphs using parsing and prompt engineering. Makes getting started easier.
Beyond RDL and LLMs, where else is PyG 2.0 making a tangible difference? What other application areas?
Oh, its applicability is incredibly broad. In chemistry, for example, PyG is used to speed up drug discovery and design new materials, helping find compounds with specific desired properties. For large spatial graphs, it's enabling next-gen data-driven weather forecasting models. It's actually been adopted by organizations like ECMWF and improving traffic prediction for smarter cities.
Wow, weather forecasting, that's cool.
Yeah. In social network analysis, it's a powerful tool for bot detection, finding communities, even spotting fake news propagation. And this is really just scratching the surface. There's this vibrant open source ecosystem around PyG now, with libraries like Quiver for distributed training, AutoGL, PyTorch Geometric Temporal for dynamic graphs. It just extends its reach constantly.
Okay, so wrapping up, what does this all really mean for you, the listener, the AI researcher, or ML engineer, trying to stay ahead in this field?
I think PyG 2.0 represents a really significant leap forward for graph learning frameworks. It fundamentally addresses those core bottlenecks, scalability, handling heterogeneity, interpretability that you hit constantly in real-world applications. It provides robust, high-performance solutions. This framework genuinely empowers you to move beyond those smaller benchmarks and confidently tackle the complex, massive dynamic graph data that defines so many modern AI problems.
So with these incredible advancements, efficiency, flexibility, all these application-specific tools, what new complex graph problems are you now empowered to tackle? And maybe thinking bigger picture, how might PyG continue to shape the convergence of GNNs with other cutting-edge AI paradigms like foundation models in the years to come? Definitely something to mull over as you continue your own deep dives.